Hi folks, today we're going to continue our discussion of relations and functions. So let's just recall that a relation, defined in the simplest way, is just a set of ordered pairs. Okay, so it's a set of ordered pairs, and usually we call that first component x and that second component y. And this defines a relationship between these two variables. Okay, so we think of the x as being the input, or the independent variable, and the y as being the output or the dependent variable. Okay, so as an example, if I take the set which includes the points 1, 2, 3, 5, 3, 7, and 4, 8, okay, this would constitute a relation. Okay, it's a set of ordered pairs. Now in this case here, I was able to just list the ordered pairs. Okay, so that's one way in which we can represent a relation. So we talk about representations of relations, and one of them is to just list the ordered pairs that are part of the relation. And another way of writing this out could be in a table of values. So 1, 2, 3, 5, 3, 7, and 4, 8. Okay. So a second way of representing a relation is to put these on a graph, especially when your two sets that you're relating both involve sets of numbers. Okay, so here I could have 1, 2, okay, and 3, 5, and 3, 7, and 4, 8. I can put these on a graph. Okay. Another way to represent a relationship between two variables is to use a formula or an equation. So let's say I want to relate to the radius of a circle and its area. So area equals pi times radius squared. Okay. So if I want to get individual ordered pairs for this relationship between radius and area, I would pick a number for my independent variable for my input r, say 2, and then from there I would use the equation to determine the output of this relation. Okay, so first of all, we have relations that are sets of ordered pairs. These can be represented in different ways. We can actually list them explicitly using a list of ordered pairs or a table of values. We can use a graphical representation, meaning use the horizontal axis to represent the input and the vertical axis to represent the output, or we can use an equation. Okay. Now there's a special type of relation, and the one that we're going to be focusing in on in the next few months, and that's what's called a function. So the way we described a function was a relation, so just a set of ordered pairs. However, for each input there would be one and only one output. Okay, so if we look at the examples we have here, we see that these examples, which all represent the same relation, these would not represent a function. Because here we see for an input of 3, I have 2 possible outputs. Okay, I can see it here in the set of ordered pairs. Or I can see it in the graph, that for x equals 3, I have 2 possible output values. So these 3 relations would not constitute a function. Whereas this one here would be a function, because if I pick a different radius value, I'm necessarily going to get a different area. Okay? So the next thing we have is we have functions, which are relations where for each input there's one and only one output. Okay? Now there's something else we're interested in, because sometimes we want to look at that set of all the inputs. Okay? So for example, let's say we have a distance versus time graph. Okay, and let's say I'm walking from my school to my house, and d is the distance from my house. Okay, I might have a relation which looks like this. Okay, so I start a certain distance away, and eventually I reach home, and my little jaunt is done. Okay, so I might be interested in the possible time values. In other words, all the possible inputs and the possible distance values. And I see here that it's limited, because say it takes me 10 minutes to complete the journey home, and I started 100 meters away from the house, I see that the list of all possible input values would lie between 0 and 10. And the list of all possible output values would lie between 0 and 100. So I can't have an output that's less than 0 or that's greater than 100 for this particular scenario. Okay, this is what we call the domain and range. So the domain is all inputs, okay, in particular the set of all inputs, and the range is the set of all outputs. Okay, so if I take example 1 here, let's call this example 1 up here, and I want to state the set which represents the domain. Okay, so first thing to know is what we use to represent a set are these braces or curly brackets. Okay, so in this scenario here, I can actually list all the domain values. Okay, and I see that my domain values consist of the number 1, okay, the number 3. Well, here the number 3 appears a second time, so I've already listed that. I don't need to list it again. And then I see that I can have an input of 4. So in this case here, I was able to explicitly list the domain values. Okay, if we look at the range values, again, because I have a finite number of points, I can just list the range values. And here I have a range value of 2, of 5, of 7, and 8. Okay, and this is what we call set notation, meaning we include all the possible inputs, all the possible outputs within a set, and that is denoted using these braces. Okay, if I look here and I take this as being example 2, okay, here I can't list all possible domain values because there's infinitely many. It could be anything starting from time 0, ending at time 10, including those 2 numbers. So this is where we use set notation again, but we use statements to define the domain and the range. So here, since there's no restrictions on the type of number t can be, okay, we say that t can be any real number. Okay, so this represents the set. That's what the curly brackets represent. This says that the variable t belongs to, okay, or another way of putting that is we say is an element of. Okay, I guess that's the more official way of saying that. Now, we saw last time that this represents the real number system. So t is an element of the real numbers, but it can't be any value in the real number system. For example, you can't pick t equals -2. Here, the experiment isn't defined for anything past 10, so there's a condition. Okay, and this is what we use to separate the condition. This represents such that. Okay, so this says it's the set of all t values that are elements of the real number system, such that, and this is where we now give our condition. And the condition here is that t needs to lie between 0 and 10, and we can include the 2 endpoints. And that's where we use inequalities to define that interval. So the way we can write that here is we say that t has to be less than or equal to 10. Okay, but it also needs to be, and now I'm going to read it from right to left, t needs to be greater than or equal to 0. Okay, and this now concludes my set. So again, let's read what this says. It says the domain of this relation is the set of all t values that are elements of the real number system such that t is greater than or equal to 0 and less than or equal to 10. Okay, and we'll have something very similar for the range values. Okay, in this case here, we'll use the variable that's being indicated. So we're saying that our distance values can be elements of the real number system, but again, there's a condition such that d is greater than or equal to 0, okay, but needs to be less than or equal to 100. And there's our range. Okay, now I called this a relation, but when I take a look at it, I notice that it's in fact a function, because for every input, okay, I see that there's one and only one output. Okay, so example 1 was an example of a relation that is not a function, whereas example 2 is a relation that is also a function. Okay, so part of the things you'll be working on will be to first of all identify whether a relation is a function or not, and then to identify the domain and the range. So the set of all possible inputs, the set of all possible outputs. Okay, in certain cases you'll be able to list the domain and range values explicitly, and in other cases you're going to use these inequalities to describe sets of numbers that are continuous, that don't just have individual values. Okay, so the last thing that we're going to look at here is a way to describe these functions. Okay, so now we'll limit ourselves to talking about relations that are functions, and we're going to talk about something that is called function notation. Okay, and what we use to define a function is we use a letter. So the standard one we use is lowercase f. If you're working with two functions, you might call the second one lowercase g, maybe the third one lowercase h. So we usually use lowercase letters to represent functions. You can use uppercase also. Okay, but what's nice about function notation is it allows you to indicate what the input is that you're putting into the function here. Okay, so let's see what I mean by that. So if we think of a regular equation, okay, the relationship between the y and the x value, between the input and output. Let's say I have a linear function here, y equals 2x plus 3. Okay, so I pick my x value, and then you can use the equation to find the y value. But let's say I tell you that y is equal to 7. Okay, well, you'd have to go back and figure out which x value gives you 7. If you take a quick look, you realize, when x is equal to 2, 2 times 2 is 4, plus 3 gives you 7. The way we use function notation is instead of writing y, okay, we call this f at x. Okay, f representing the particular function that we're working with, and we're specifying that the input to this function will be an x value. Okay, so if I'm looking for the y value when x is equal to 2, I would write f at 2. And that's equal to, well, 2. So what I do now is wherever I see an x in my equation, I now replace it by 2. So 2 times 2 plus 3, and so f at 2 is equal to 7. So instead of just saying y is equal to 7, I use this notation here, f at 2. So this whole thing here represents my y value, but what's nice about it is that it first uses the name of the function. In this case here I've called it f, and it also indicates what the input was that produced the output of 7. So we're going to work a little more with this in a second, but I want to talk a bit again about this idea of a function. And one way that we think of a function, okay, especially when we're thinking about an equation, is we think of a function as a machine. Okay, so think of say a machine that blends ingredients. So you would put all the ingredients, say eggs, flour, milk, and you would put it into the machine, and what the machine would produce as an output would be the batter that you could use to make your cookies. Okay, so we think of this machine as receiving an input, which is our x value. The machine is going to do something to that x value, and it's going to produce an output. Okay, and if this machine is called f, the output y is written f at x. So we say this here, f at x. Okay, now If it was the mixer we were talking about, what would it do to take those eggs, flour, and milk and turn it into batter? Well, it would use electricity and paddles and all that to mix everything together to produce the output, which is the batter. What does a mathematical function do to an input to create an output? Well, it uses mathematical operations. So in this case here, what were the operations used by this machine to produce an output? Well, it used multiplication, so it multiplied the input by 2, and then it added 3 units to that. Okay, if I had a function y equals 2x squared plus 3x, well, this is a more complicated machine. What does this function do to create an output? Well, you give it an input of x, and it's going to take that number, square it, then multiply it by 2, and then add 3 times that number to it to get your final output. Okay, so what a function does is it receives an input, it performs a bunch of mathematical operations on that input to create a single output, and that's what's important. There's one and only one output. Okay, so last thing I want to look at here is I just want to show you how one could work with function notation. Okay, so let's say I define some function. I say f at x. Okay, so what this function does is it takes the input x and it's going to perform the following operations. So say 2x squared minus x. So whatever my input is, that's what we find in bracket as our input. What this function does to that input is it squares it, multiplies it by 2, and then subtracts it by the original number. So I can choose to determine a particular output. I could choose to determine f at, let's start with a positive number, f at 2. How would I calculate? So remember that this represents the y value, the output, okay, when the input is equal to 2. And I use my equation to determine that output. So wherever I see an x, I'm now going to replace it by 2. So 2 times 2 squared minus 2. So what do we have? 2 times 4 is 8 minus 2 equals 6. Okay? If I want to determine f at negative 3, in other words, the output when the input is negative 3, well, what do? I replace my x values by negative 3. Now this is where you'll notice I always take my input and always put it in brackets, even though I didn't really necessarily need to do that here, okay, because BEDMAS would have taken care of everything. Here it's important that I have brackets around the negative 3, because it's the whole number x that is being squared. Okay, so we know that if I don't put the brackets and I square negative 3, I don't get the same answer as if I do put the brackets in. So please keep that in mind. Okay, and so now, the machine is going to compute all these things. So 2 times 9, and then plus 3. And so here we have 18 plus 3 is 21. Okay, now I could find f at 2 minus f at 1. Okay, so notice here I'm taking the difference of 2 different function values. So the first thing you need to do is determine each individual function value. Well, I've already determined f at 2, so that's equal to 6. I'm not going to redo that. And now let me subtract f at 1. Notice here, I'm subtracting this expression f at 1, but that expression has a few components in it. That's why I'm going to make sure I use brackets. So now I can input 2 times 1 squared minus 1, and now I'll just keep simplifying. So here we have 2 minus 1 is 1, and then finally 6 minus 1 is 5. The last thing I'll show you is something very interesting. Okay, but I want you to keep in mind what this equation means. It's a recipe, it's a formula that tells you what this function does to an input. So whatever my input is, I have to square it, multiply it by 2, and then subtract the original input. So let's say I want to find f at x plus 1. Let's say the input itself is a variable input, something that changes. Okay? As long as I follow my recipe to a T, I won't make a mistake. So let me see what my recipe tells me to do. It tells me to take my input, whatever it is, and square it. So I'm going to take my input, x plus 1, and square it. Then I need to take that and multiply it by 2. So I'm going to multiply this by 2. And then I have to subtract whatever the input is. Okay? Again, I hope you're seeing that putting the input in brackets is going to be vitally important to make sure I don't make any silly mistakes. Once I've done my inputting, I can now use algebra to simplify this. So here, okay, and of course this is not equal to x squared plus 1 squared. You got to use your old square the first, square the last, twice the input of first and last, so 2 times x, and then plus 1. I like to write it in this form here. Then let's simplify this, minus x minus 1. Okay, do distribution, so 2x squared plus 4x plus 2, and minus x minus 1. And now I can give a final answer, 2x squared. We've got 4x minus x, so plus 3x, and then 2 minus 1 is 1. And there we go. Okay, so when we're using function notation, let's keep in mind what everything means. Okay, this expression here represents your y value for whatever the input is in the bracket, and then this is the equation. These are the operations that you're performing in order to achieve your output based on your input. Okay, so that's it for now, and just work on the assigned questions.